So welcome to this video on both complex number theory and parallel RLC AC circuits. In the first part we're going to look at polar and rectangular form, we're going to look at division, and we're going to look at converting between rectangular and polar and vice versa and their advantages. And later on we'll be looking at parallel RLC circuit application of the theory that we've learned with waveform analysis. So we'll be finding currents, impedances, reactances, voltages. So I hope you enjoy this video. So we have a polar voltage, it's an inductor voltage, 500 millivolts at an angle of 53.13 degrees. And polar numbers have a modulus and an argument, can be written in different ways. Could be a magnitude and an argument, or an absolute value and an argument, but the best way to think of it is modulus and argument, but what it really is a hypotenuse and an angle. But when you think about this polar number, the point that it represents can be expressed in rectangular form. So we have 300 plus 400J millivolts, which is real plus imaginary. And the best way to think of a rectangular complex number is an adjacent and an opposite side. Finding reciprocals of complex numbers, which is useful for parallel impedance calculations. So we've got polar reciprocal and rectangular reciprocal, and we'll do them next to each other. So we have a inductive impedance of 100 ohms at 90 degrees. To find the reciprocal of that, 1 over ZL is 1 over 100, and we do 0 degrees, take away 90, because the number 1 has no phase, it's just a real number. So that's 0.01 at an angle of 0, take away 90 degrees. So we divide the moduli, or the moduluses, and we subtract the arguments. So that is 0.01 at an angle of minus 90 degrees in Siemens. We have the same impedance in rectangular form, which is 0 real plus 100J imaginary. So that's just 100J ohms. And it's worth remembering that 1 over J is minus J, and 1 over minus J is J. And that comes from the fact that J squared over J is minus 1 over J. But J squared over J is just J. So 1 over ZL in rectangular is 1 over 0 plus 100J, which is just 1 over 100J. And that's the same as 1 over 100 times 1 over J, which is 0.01 times minus J. Then we just tidy that up a bit. So 1 over ZL in rectangular form is minus 0.01J ohms to the minus 1, or Siemens. So the bottom two numbers, one's polar, one's rectangular, but they mean the same thing. So minus 90 degrees goes with minus J, and plus 90 degrees goes with plus J. Polar division. It's useful to find currents using Ohm's law, and it's quicker and easier than rectangular form division. So we have a current I is V over Z. We have a voltage of 100 volts with no phase shift and an impedance of 75 ohms at minus 58 degrees. So to divide polar numbers, you divide the top modulus by the bottom, and then you do 0 degrees, take away minus 58, so that becomes positive 58 degrees. So it's really easy to do. And with polar multiplication, you multiply the two moduli or amounts together, and you add the angles instead of subtracting. Rectangular division then. It's useful to find currents using Ohm's law, but it's a little more complicated than polar division, but it's still not too bad. So I is V over Z from Ohm's law. We'll have a voltage and an impedance. The voltage is 100 volts with no imaginary part, and the impedance is 39.744 take away 63.604 J. in this example. But you cannot divide by a complex number, so we have to multiply by the conjugate divided by itself. And then the overall denominator will become real, so we can do the division. So the bottom terms, 39 times 63j, approximately, when we expand out, added to 39 times minus 63j. When we add them together, they equal 0. So the outer and inner terms don't feature at all in the answer. And then we're left with the two imaginary parts. Minus 63j, roughly, times 63j is minus 63 times positive 63 times j squared. And that's just 63 squared, with a minus sign in front of it, times minus 1. So what we end up with is just the imaginary parts squared for those two terms, which is really easy to do. And don't forget, of course, the real part times the real part of the denominator. So when you multiply by complex conjugates to divide, the overall denominator is just the real part squared added to the imaginary part squared. So multiply out the top, and we've already figured out how to do the denominator. Then we end up with those numbers on the numerator, real and imaginary, divided by a real denominator. And then you just split it up and divide them both by 5,625.054. And that gives us 0.7066 plus 1.131 J amps. So it wasn't too bad, so we've done rectangular division. It's always best to convert to polar. Well, it's quicker anyway to do division. So polar to rectangular conversion. It's useful to be able to convert between polar and rectangular and the other way. It's useful when addition is needed because rectangular is really easy to add. So we've got a current in polar form of 1.3 recurring amps at 58 degrees, which is a hypotenuse and an angle. And we can see it there. But don't forget that the real part of the rectangular conversion is the adjacent side, and the imaginary part will be the opposite side of a right-angled triangle. Cosine always goes with adjacent, and sine always goes with an opposite side. So there we go, we can see the adjacent is the real part and the opposite is the imaginary part, and in polar form we're given the hypotenuse and the angle. Adjacent is equal to hypotenuse times adjacent over hypotenuse, because the hypotenuses cancel. But adjacent over hypotenuse is the cosine function. That's what it is. So the real part is going to be the polar modulus or hypotenuse times the cosine of the argument. And similarly, the opposite is equal to the hypotenuse times the opposite over the hypotenuse, because the hypotenuses cancel, but opposite over hypotenuse is the sine function. So the imaginary part of our rectangular conversion will be the polar modulus, or the hypotenuse, times the sine of the angle. But don't forget to put a j on the end. So the rectangular version of our polar number is 1.3 recurring cos 58 degrees plus 1.3 recurring times the sine of 58 degrees with a j to indicate it's the imaginary part. So that is equal to 0.7064 plus 1.131 j amps. Just another quick example. If an impedance Z is 75 ohms at minus 58 degrees, then find the real and imaginary by doing 75 cos minus 58 degrees for the real, plus 75 times the sine of minus 58 degrees for the imaginary. And don't forget to put the j and the units. Just use a calculator for this, and we end up with 39.744 minus 63.604 j amps. And there's the triangle representing rectangular and polar of the same number. And remember, it's just the same triangle. Whether you use polar or rectangular, it's just a right angled triangle. Rectangular to polar conversion. Say we have a current of 0.7064 plus 1.131 J amps like we saw earlier. That's rectangular form, so it has a real and an imaginary part, or an adjacent and an opposite side to it. And whenever you know two sides of a triangle and you want to find the hypotenuse, we use Pythagoras' theorem. So the polar version of our rectangular current is the real squared plus the imaginary squared, square rooted, which is Pythagoras, and the argument, or the angle, is tan to the minus 1 of real divided by imaginary, or opposite over adjacent. So that's 1.3 recurring is the polar modulus, and the argument, or angle, is tan to the minus 1 of opposite over adjacent, which is tan to the minus 1 of imaginary over real, which gives us the polar argument, or angle, of 58 degrees. So the polar version of our rectangular current is 1.3 recurrent amps at an angle of 58 degrees. Just a word of warning, if we have a positive real part, as shown on these two graphs, then we would use tan to the minus 1 of opposite over adjacent to get our polar argument. But if you have a negative real part, which you would in mathematics, then what we have to do is the same thing, but we need to add 180 degrees to the answer to our polar argument. On the two left-hand graphs, the angles indicated would be confused with each other, but it's not an issue in electronics. It doesn't affect us in electronics as we never have a negative real part, and our phase differences are between 90 and minus 90 degrees with resistors, capacitors and inductors. So polar versus rectangular, which is best? And it all depends on what you need to do. Polar is really good for division, like currents, I is V over Z, or for finding reciprocals for parallel impedances. It's nice and quick and easy for division and multiplication. For polar multiplication, V equals IZ, Ohm's law. It's really good for that. And when we do multiply two polar numbers, we multiply the amounts, or the moduli, and we add the arguments, or the angles. So it's the opposite of division, of course. Rectangular form is really good for series impedances, as in addition, where you add the real parts together and you add the imaginary parts together. And rectangular is really good for subtraction in the same way, where you would subtract the real parts and subtract the imaginary parts. It's great for finding voltages in between series components, where a voltage we could call Vx is the supply voltage take away a voltage drop across a resistor, say. So, parallel RLC AC theory, we're going to find reactances, an impedance, the currents and the phase angle. We've got 100 volts supply voltage at 50 Hertz with no phase shift, because with parallel we have the same voltage across the components but different currents through them. And Vs, the voltage supply, is the reference phasor on the x-axis, and the current through the resistor is also in phase with the supply voltage. We've got 220 ohm resistor, 318.3 millihenry inductor and a 6 microfarad capacitor roughly. So the reactances, XL is 2 pi FL, which is 2 pi times 50 Hertz times the inductance. And inductors have no real part, so it's plus 100 J ohms, or 100 ohms at 90 degrees in polar form. The capacitive reactance is 1 over 2 pi FC, and that comes out as 0 minus 500 J ohms, as you can see from the phasor on the top right, and that's 500 ohms at an angle of minus 90 degrees. Capacitors and inductors have no real part in theory, only imaginary parts. And then the resistance has no imaginary part, it's purely real. So that's 220 ohms plus 0J, or in polar form, 220 ohms at an angle of 0 degrees. In parallel, to find the total impedance, we use the reciprocals formula. 1 over Z total is 1 over ZR plus 1 over ZL plus 1 over ZC in Siemens, or ohms to the minus 1. So it's useful to be able to find reciprocals because we find the reciprocal of each component's reactance or impedance. We add them together, then we take the reciprocal of that to get the total impedance. And then we can find currents, and when we know currents, we can find voltages in series circuits. So a quick recap of our reactances and resistances. We're going to compare polar to rectangular form for the calculations for this circuit. So in polar form, 1 over Z total is 1 over 220 ohms at 0 degrees plus 1 over 100 ohms at 90 degrees plus 1 over 500 ohms at minus 90 degrees. That's the reciprocal of the total impedance. In rectangular form, we have 1 over 220 plus 0J ohms for the resistor, 1 over 0 plus 100J ohms for the inductor, and for the capacitor, 1 over 0 take away 500J ohms. So the inverse of the resistor is 4.54 recurring times 10 to the minus 3, and then the inductor is 0.01 at an angle of minus 90 degrees, remember. And then for the capacitor, 0.002 at an angle of positive 90 degrees. In rectangular form, we have the same resistive impedance, the reciprocal of that, and then we have 0.01 times minus J for the inductor, and then we have 1 divided by 500, which is 0.002 times positive J for the capacitor. Doing the same on the left hand side for polar, looking at the reactances, the capacitor and inductor. For the inductor, 1 over ZL is 1/100th at an angle of minus 90 degrees, and then opposing that is 2/1000ths at positive 90 degrees. So you can only add polar numbers together if they're in the same plane, like on the same straight line. Then it's a tug of war between these two to see which one's stronger. So we've got 10,000ths down, take away 2,000ths up. So the resultant of the reactances is going to be 8,000ths downwards at minus 90 degrees. But we still can't add that to the 1 over ZR yet, because that is not in the same direction. So we have to use Pythagoras. So 1 over ZT is 4.54 recurring times 10 to the minus 3 plus 8 times 10 to the minus 3 at minus 90 degrees in polar form. Then in rectangular form, we've got 4.54 times 10 to the minus 3, and we simply add the blue to the red. It's very similar, but you'll notice that it's very difficult to add in polar form, especially where resistors are involved. So to find 1 over Z total, we've got 8 times 10 to the minus 3 at minus 90 degrees. So that's certainly a negative value. To find 1 over ZT in terms of its real and imaginary, which is technically rectangular anyway, even though we were trying to use polar, we need to use Pythagoras. Because we cannot add the real part to the imaginary part, because they're not on the same plane. and that comes out as 9.2011 times 10 to the minus 3 in polar form at an angle of, we know it's a negative angle because it's pointing down, tan to the minus 1 of opposite over adjacent. And even though the amount is 8 times 10 to the minus 3, it's downwards at minus 90 degrees, so it's certainly a negative number. So that's minus 8 milli divided by 4.54 occurring milli. Gives us an angle of about minus 60.4 degrees. So 1 over zt is 9.2011 times 10 to the minus 3 at an angle of minus 60.4 degrees. But we haven't quite got the total impedance yet. We need to take the reciprocal. So we do 1 over 9.2 times 10 to the minus 3 for the modulus. That's 108.68 ohms. And then we do 0 take away minus 60.4, which is positive 60.4 degrees. So that's the total impedance in polar form. But you have to use rectangular to some degree, even when you're doing polar. Then back to rectangular. Zt will be the reciprocal of 1 over zt. So that's 4.54 occurring times 10 to the minus 3, which is the real part, minus 8 times 10 to the minus 3j, which is the imaginary part. But as we said earlier, we have to multiply by the conjugate of the denominator divided by itself. So zt is equal to what we just had times the conjugate of the denominator. So instead of minus 8 times 10 to the 3, it becomes positive 8 times 10 to the minus 3j. But the shortcut, of course, is that the new numerator will just become the conjugate, and the new denominator is just the real squared added to the imaginary part squared. So it's really quick and easy to do, even though it looks awful. And then the denominator is real, so we can divide by a real number. We cannot divide by a complex number without using conjugate multiplication. Just use the calculator to find out what that is. We're squaring the two terms on the bottom to find the new denominator, and that's 8.466 times 10 to the minus 5. We already had the numerator, which was the conjugate, and then you just split it up and divide both sides by 8.466 times 10 to the minus 5, which I'm storing in a memory location on the calculator. So the real part is 53.69, and the imaginary part is 8 times 10 to the minus 3j divided by 8.466 times 10 to the minus 5. 94.495j, don't forget the j. So they are equivalent to each other in polar and rectangular, hopefully, but we need to convert one to the other to check that that's true. So we'll convert the rectangular version into polar using Pythagoras and tan to the minus 1. So adjacent squared plus opposite squared at an angle of tan to the minus 1 opposite over adjacent. So it's pretty simple, really. It's just about triangles. Square the real, square the imaginary, add them and square root, and it's 108.68 ohms at an angle of tan to the minus 1, 94.495 divided by the adjacent, 60.4 degrees. So they're both correct, but you just have to decide which form you'd like to use, polar or rectangular. Now we know the total impedance, we can find the total current, I is V over Z from Ohm's law. So the supply voltage divided by the total impedance gives us the total current at 100 volts as a reference, so there's no phase shift, divided by 108.68 ohms at an angle of positive 60.4 degrees. So do modulus divided by modulus, gives us 920 milliamps roughly, 0.92 amps. And for the argument, or the angle, you subtract. So at 0, take away 60.4, which is negative 60.4 degrees. So our current is lagging the supply voltage. And we can see that we got roughly the correct answer with a bit of rounding. And I also had an extra resistor with the inductor, which would have changed things a little bit, because then it simulates better. You can notice all of these currents, and we're going to check that they're correct through calculation. So the current through the resistor is voltage over resistance, 100 volts divided by 220 ohms, no phase shifts in either. And that's 0.45 recurring, which is 454.54 recurring milliamps at an angle of 0 degrees. And we can see we got that right, at least the modulus is correct. And the inductor voltage, I is V over Z, so 100 volts divided by 100 ohms at an angle of 90 degrees for the inductor. So that's 1 amp at an angle of minus 90 degrees. So that's lagging. We can see we got the modulus correct. And then for the capacitor, I is V over Z, so 100 volts divided by 500 ohms at an angle of minus 90 degrees. So that's 0.2 or 200 milliamps at an angle of 0, take away minus 90. And we've got that correct. So on multisim, we'll simulate, then we'll press pause at the top left, then we'll click on grapher, then we will zoom all axes, and we'll choose a suitable time after it's started, 100 milliseconds to about 150 milliseconds, say. And we're going to use cursors to find where the supply voltage starts and when the current starts. So you need to be quite accurate about where you can either use the peaks or where they cross their own x-axis. And the more accurate you are, the better. And then we'll observe the difference in time between the supply voltage and the total current, 3.35 milliseconds. And then we can work out the phase difference, because the time difference compared to a period is the same ratio as the phase difference compared to 360 degrees. So that means the phase difference is the time difference times 360 divided by 20 milliseconds at 50 Hertz. So we'll put those numbers into the calculator, and it should tell us that we've got an angle of about 60.4 degrees. That's not too bad, considering this was from observation and we couldn't get an exact time difference. And we can see the supply voltage is leading the total current as we thought, or the current is lagging. And then we'll look at the currents. So we've got the resistor current, inductor current and capacitor current. You can turn them on and off in multisim. We can see here where the resistor current starts and the supply voltage starts at this point. It first goes positive, so that's the reference. And then if you notice, the capacitor current is at its maximum value, so it's already started. So it's leading by 90 degrees. It's leading the total current, it's leading everything, but it's leading the supply voltage by 90 degrees. Then the inductor current is at its minimum value, lagging the resistor current and the supply voltage. We can put on the total current in dark blue, which we worked out earlier. And then if we subtract IC from IL, we can then resolve this phasor to find the total current on the phasor diagram. And it is 60.4 degrees behind when the resistor current occurs and when the supply voltage occurs. And we can put the supply voltage on this graph too. And that's the completed phasor. So it's all worked pretty well, to be honest. There you can see all of the waveforms, and all our calculations have been correct. So thanks so much for watching. Please leave your comments below and have a go yourselves. All the best.